In this problem we're given a radical function, its graph, and a small table of values. We're asked to state the domain of the given function in interval notation. Let me start by saying that using a table of values or a graph to find the domain of a function is not the most accurate approach. As a guide, they're very helpful, but the representation of the function that's best in finding the exact domain of a function is its equation. Think of the domain of a function is the set of all x values or possible inputs for which you will get a defined output. So for example, because this equation involves a square root, let's discuss the meaning behind the problem before I show you how to get to the answer. Getting the answer is very easy, but if you don't understand why the answer makes sense, you will not be able to do problems similar to this one. You'll only be able to do this exact problem. So because this equation involves a square root, let's define what it means for something to be in the domain as opposed to out of the domain of a square root function. For example, given the equation for my function f, let's plug in x equals 0. At x equals 0, we would have that f of 0 is equal to the square root of 0 plus 2, which simplifies to be the square root of 2. This is an example of an x value that's in the domain of the function, because my output, square root of 2, can be calculated in what's called the real number system. The square root of 2, if you were to type that in your calculator, you would get about 1.4142, and this is why in the table of values, when you see an x value of 0, because the output at x equals 0 comes out to be the square root of 2, this is why you see 1.4142 in the table of values. That's a rounded version of the square root of 2. Likewise, on the graph, if you look at the point on the graph whose x value is 0, you see that the y-coordinate is between 1 and 2, about 1.5, but more specifically about 1.4. Remember, the graph, you can only estimate the output. On a table, the output is rounded. So with this table and this graph, you can only get an estimate of what the output would be, whereas the equation tells me that the output is exactly the square root of 2. Let me give you an example of an x value that's not in the domain. This would be easy to see on the table. Here are some examples of x values for which the function is undefined. They show up this way in the table. They also show up on the graph in the following way. If I was to ask you what is the output when x is negative 5, looking over at x equals negative 5, you see that there's no point corresponding to that x value. The fact that there is no point means the function is undefined. The problem with a graph, however, is that no graph is ever complete. The graph could actually exist outside the window for which the graph was drawn. So again, the graph is just a guide. The real way to find the domain is to actually use the equation. So back to the equation, if I choose x to be negative 5, we get that f of negative 5 would be negative 5 plus 2, which simplifies down to be the square root of negative 3. Now, the square root of negative 3 does have a definition. If you've ever had a lesson in complex numbers and the imaginary number I, you may know this. But the intent of this problem is to state all the x values for which the outputs exist in what's called the real number system. So it turns out the reason that the output is not in the real number system is because that the radicand, meaning the number under the radical, in my case my radicand is this, whatever the expression is under the radical is called the radicand, and the radicand needs to be positive or 0 for the output of this function to be defined in the real number system. If you think about what square root means, it means that there must be some number that when you multiply it by itself, you get negative 3. And the rule, of course, is that the number you put here has to be the same number you put here. So if you put a positive number here, you have to put a positive number here, in which case you'd have a positive times a positive, which can't be a negative. Your other option is to put a negative number here. But if you put a negative number here, you have to put a negative number here, and we know that a negative times a negative is also a positive, so it cannot be negative 3. So there's no real number that you can put here so that when you multiply it by itself, you get negative 3. So for this x value, negative 5, the function would be undefined, so the x value of negative 5 is not in the domain. So we need to write an answer here that includes x equals 0, but excludes x equals negative 5. So all this just to find whether these two numbers are in the domain or not. We have an infinite amount to consider. So the right way to do the problem is to copy the radicand down, the x plus 2, and simply state what we need to happen. We need the radicand to come out to be a positive number, that means greater than 0, or it actually can be 0, because if the radicand came out to be 0, you'd have the square root of 0, which in math is defined to be 0. In fact, in our problem, that happens at x equals negative 2. If you replaced x with negative 2, your radicand would be negative 2 plus 2, or 0, and the square root of 0 is defined to be this right here, an output of 0. So this right here happens at the equality, when x plus 2 comes out to be 0. Also on the graph, it happens to be the endpoint of our graph. When x is negative 2, the output is 0, and that's the point here, negative 2 comma 0. So all I have to do is set the radicand greater than or equal to 0. I can solve in this case by simply subtracting the 2 on both sides. When you add or subtract with an inequality, you need not change the sign on the inequality. So my answer is x is bigger than or equal to negative 2. And again, the table on the graph will help as a check. Notice that I have answers as outputs when x is either negative 2 or bigger than negative 2 on the table. And notice on the graph that the graph exists everywhere to the right of x equals negative 2. That means if you're to the left of x equals negative 2, the function's undefined. But if you're at negative 2, and this is what that line means, when x is negative 2 or bigger than negative 2, meaning to the right of this red line I drew, then your function actually is defined. You're actually getting points. For every x value, you see some corresponding output. Now, one thing to notice is that I've expressed my answer in inequality notation, but the direction is set to state it in interval notation. So assuming you know interval notation, we need to express numbers that can be equal to negative 2, so that would require a bracket to indicate that the negative 2 is included in the domain. That would be the smallest number in my domain. Because the graph goes to the right forever, because we want all numbers greater than negative 2, and that goes on forever, we use an infinity symbol. And then since you can't actually reach infinity, in fact it's not a real number, we put a parenthesis here. If this is a computer-generated question, it's likely that you can enter infinity using 2 lowercase o's on the keyboard. Now if we give you a more complicated function, hopefully you realize it's the square root that's causing this issue for some x values to give valid outputs and other x values that produce no valid output of the function. So if we were to change the equation and make it more complicated, such as negative 3 subtract 5 times the square root of the quantity x plus 2 all divided by 1,000, hopefully you see that the domain would still be exactly the same. And the reason is it's only the radical that's going to change the domain. As long as this radical is defined as a real number, you can take any real number and multiply by 5. You can take any real number and subtract it from negative 3. You can take any real number and divide by 1,000. So adding all these features to the equation makes no difference relative to the domain. With this structure, it's only the radical that creates the issue, and the issue is when the radicand comes out to be a negative number. So our strategy was to simply make sure that that radicand never comes out to be negative. We did this by saying, please make sure that my radicand, which is x2 in my case, comes out to be positive, bigger than 0, or it could be 0.